The morning of September 27, 1959, off the coast of New London, Connecticut, a submarine longer than a football field and a half cuts through the Atlantic on her very first full-power run. Her name is USS Triton. She is 447 feet long, displaces nearly 6,000 tons on the surface, and she has just done something no submarine designer thought was necessary. Buried in her hull are not one, but two complete nuclear reactors. Here's the contradiction that should stop you cold. Every other nuclear submarine ever built by the United States Navy, before or since, runs on a single reactor. One core, one engine room, one source of power. The Navy's own engineers considered a second reactor wasteful, expensive, and unnecessary weight. Yet Triton carried two, welded into a hull so long that the shipyard building her had never handled anything like it. On that September morning, she blew past 30 knots, well in excess of what her own designers had promised. So why did one of the most advanced navies on Earth decide that a single nuclear reactor, the technology that was already revolutionizing submarine warfare, simply wasn't enough for this one boat? The answer is a story about a mission nobody could satisfy with existing engineering, and about engineers who solved it by doing something nobody else dared try. To understand why Triton needed twin reactors, you have to understand the job she was built for, and that job had nothing to do with hunting enemy ships. In the early 1950s, the U.S. Navy faced a specific tactical problem. Soviet long-range bombers were improving fast, and a carrier task force steaming across open ocean needed early warning of an incoming air raid long before its own radar could see the threat. The solution the Navy settled on was the radar picket submarine, a boat that would run on the surface well ahead of the carrier group, its radar mast scanning the sky for approaching aircraft and relaying the warning back by radio. This was a strange assignment for a submarine. Pickets weren't supposed to hide. They needed to run on the surface at high speed, day after day, keeping pace with a fast carrier task force that could sustain 30 knots as long as its escorts could. The Navy had already converted several fleet boats, submarines like Reactors and Tigrone, into radar pickets by stripping out armament and cramming in air search antennas, and the results were sobering. Their diesel engines, built for economical surface cruising rather than sustained sprinting, wore out fast under the strain of continuous high-speed running, and their limited fuel bunkerage meant they couldn't stay on station more than a few days before turning home for more. But what they didn't know was that the technology already being tested a few hundred miles up the Connecticut coast was about to make the entire diesel picket concept obsolete overnight. Then came USS Nautilus, commissioned in January 1955, proving that a single nuclear reactor could give a submarine virtually unlimited range and could sustain high speed for as long as her crew's food held out. Nautilus solved the endurance half of the picket problem overnight. When the Navy ordered its first purpose-built nuclear picket submarine in October 1955, under the design designation SCB-132, the requirement was blunt: match a fast carrier's sustained speed indefinitely without refueling in a hull large enough to carry a proper air search radar and combat information center. Nuclear power could clearly deliver the endurance. The question the engineers still had to answer was whether a single reactor, even one as capable as Nautilus's, could deliver the speed a hull this size would need. Here's where the math turned against a single reactor design. Existing American submarine reactors, like the S-3W plant powering the Skate-class boats, produced roughly 6,600 shaft horsepower, enough for a lean attack submarine hull under 300 feet long. Triton was never going to be lean. To carry a powerful new air search radar, a large combat information center, extra berthing for a bigger crew, and enough structural strength to survive sustained high-speed pounding on the surface, her hull had to grow to 447 feet and nearly 6,000 tons surfaced, dimensions that made her, at the time of her commissioning, the largest submarine ever built. A hull that size pushing through water at 27 to 30 knots doesn't just need more power, it needs dramatically more power, because water resistance against a hull climbs roughly with the cube of its speed. Push a submarine twice as fast, and you don't need twice the horsepower, you need something closer to 8 times as much. Naval architects at Electric Boat and the Bureau of Ships ran the numbers and found a hard ceiling. A single S-3W-type plant, scaled up as far as contemporary submarine reactor technology allowed, still couldn't push a hull this large to the sustained speeds the picket mission demanded. Not without a reactor core so oversized, it would have consumed more internal volume than Triton's entire radar and combat information suite combined. And speed wasn't the only requirement working against the engineers. A picket boat operating far from friendly ports, alone ahead of a task force, could not simply go dead in the water if her single reactor tripped offline from a mechanical fault, a design flaw, or battle damage. For an attack submarine that could limp home on battery power at a few knots, a reactor casualty was inconvenient. For Triton, sitting exposed on the surface hundreds or thousands of miles from the nearest friendly port, unable to submerge fast enough to hide and unable to keep pace with the task force she was supposed to be screening, a single reactor casualty could strand a 6,000-ton, $100 million warship in open ocean with no way to get home under her own power. The real breakthrough came when planners at the Bureau of Ships stopped trying to solve this as one problem and split it into two, treating speed and reliability as separate engineering questions with separate answers. Commander Will Adams, who would later serve as Triton's executive officer, understood the stakes of pushing new technology into an unforgiving mission better than most. The Navy was asking for a submarine that had to be simultaneously the fastest, the largest, and the most reliable boat in the fleet, and existing single-reactor engineering could satisfy at most 2 of those 3 demands at once. Choose speed and size, and you sacrificed the safety margin. Choose reliability and size, and you built a boat too slow to keep up with the carriers she was meant to protect. Every path through the design space using a single reactor core dead-ended somewhere. The answer that finally broke the deadlock wasn't a bigger single reactor, it was 2 smaller ones working together, and the engineering required to fit them both inside one hull would push submarine construction to its limits. The Navy's Bureau of Ships, the Atomic Energy Commission, and General Electric had already been developing exactly this kind of answer through a joint effort called the Submarine Advanced Reactor Program. Rather than trying to scale a single core up to unprecedented power, engineers designed a compact, efficient pressurized water reactor called the S3G, tested first as a land-based prototype at the Kesselring site near West Milton, New York, beginning in 1958. The seagoing version of that design, designated S4G, would go into Triton not once but twice, 1 reactor forward and 1 reactor aft, each driving its own steam turbine and its own 5-bladed propeller through an independent shaft. Think of it less like doubling an engine and more like giving the ship 2 separate hearts, each capable of keeping the whole body alive on its own. Each S4G reactor produced around 22,000 shaft horsepower, and together the plant was rated at a combined 78 megawatts of thermal output, enough to give Triton an installed power rating of 34,000 shaft horsepower, roughly 5 times what a single Skate-class reactor could deliver. That was the speed problem solved. The redundancy problem solved itself as a byproduct of the same design. If one reactor plant had to be shut down for any reason, Triton could still make way, still generate emergency power, and still bring her crew home on the other.
Fitting two complete nuclear engineering plants into one hull, though, was not simply a matter of copying a working design and installing it twice. The S4G plant used horizontal steam generator U-tubes, an unusual configuration for a submarine reactor at the time, along with a de-aerating feed tank, a feature found on almost no other submarine plant in the fleet. Both changes needed to make two compact plants fit the available hull volume without doubling the length of machinery spaces beyond what Triton's frame could support. Electric Boat's own engineers openly acknowledged that Triton's sheer length presented problems throughout construction that a standard single-reactor hull never posed, from structural framing around two separate reactor compartments to the sheer logistics of routing steam lines, electrical runs, and shielding through a vessel stretching the better part of a city block. However, the biggest challenge was still ahead, because a blueprint solving all of this on paper still had to survive contact with an actual shipyard floor, actual steel, and a workforce that had never built anything like it before. Weight distribution became its own puzzle. Nuclear shielding is heavy, and Triton needed two complete sets of it, positioned fore and aft rather than concentrated amidships, which meant naval architects had to rebalance the entire hull's trim calculations around two heavy machinery spaces instead of one, rather than the single centrally weighted engine room every other American nuclear submarine used. Every pipe run, every set of control cables, and every ventilation duct running the length of the ship had to cross between two separate reactor compartments instead of one, and each of those crossings needed its own shielding and its own isolation valves so that flooding or damage in one engineering space couldn't cripple the other. It was, in effect, building two submarines worth of nuclear plumbing and then finding a way to make them share a single outer hull without either plant compromising the safety of the other. The crew training pipeline had to change too. Every engineering officer and enlisted nuclear operator assigned to Triton trained directly at the S3G prototype in West Milton, New York, because Triton was and remains to this day the only Western submarine ever built with a two-reactor propulsion plant. There was no other boat in the fleet where sailors could learn this system. Captain Edward L. Beach, Jr., Triton's first commanding officer, and his executive officer, Will Adams, both went through months of specialized instruction at that prototype before they ever set foot on the finished submarine, because the plant they were about to command didn't exist anywhere else to practice on. Electric Boat proved plank by plank and pipe by pipe that two independent nuclear plants could be shoehorned into a single pressure hull without compromising the very quality submarines depend on most: watertight, structurally sound integrity under deep diving pressure.
The timing of Operation Sandblast had never been an accident. Navy planners wanted Triton's feat completed just before the four-power Paris summit between Eisenhower and Soviet Premier Nikita Khrushchev in May 1960, hoping a triumphant circumnavigation would hand the American delegation a fresh symbol of technological supremacy heading into the talks. The mission delivered exactly that engineering triumph on schedule, but the political payoff never arrived. Just days before Triton surfaced, a CIA U-2 spy plane was shot down over Soviet territory, its pilot captured alive, and the resulting diplomatic collapse scuttled the Paris summit entirely. Most of the celebrations planned for Triton's return were quietly canceled. The New York Times still ran a tribute describing the feat in print as a triumph of human prowess and engineering skill. But what they didn't know was that the diplomatic disappointment wouldn't diminish what the engineering itself had already proven, regardless of whether Washington and Moscow ever sat down at that table in Paris. Triton returned to Groton on May 10, 1960, to what welcome remained, and Beach personally received the Legion of Merit while the ship earned a Presidential Unit Citation from Eisenhower. Yet within a year, her original mission had already evaporated.
carrier-based airborne early warning aircraft, faster and cheaper to operate than a 6,000-ton submarine, made the radar picket role obsolete almost as soon as Triton mastered it. In March 1961, she was reclassified as a standard attack submarine, a role her enormous hull was never optimized for. The Navy never built a second twin-reactor boat. The added cost, complexity, and crew training burden of maintaining two separate nuclear plants outweighed the redundancy benefit once single reactor cores grew powerful and reliable enough on their own to satisfy every mission that followed. The real value of Triton's engineering had never really been about the picket mission in the first place. It was about proving, under conditions no peacetime trial could replicate, that American nuclear engineering had matured to the point where two independent reactor plants could run in parallel across every ocean on Earth without a single failure serious enough to force a surfacing. That was a message aimed less at any single tactical requirement and more at what a nuclear-powered submarine, in general, was now capable of.
Triton's keel went down on May 29, 1956, at Electric Boat's Groton, Connecticut yard. She launched on August 19, 1958, immediately claiming the title of largest submarine ever built, a record that had belonged since World War II to Japan's giant I-400 class submarine aircraft carriers. Fitting out and final systems testing took another 13 months before commissioning on November 10, 1959. And by the time she ran her full-power trials that September, the twin-reactor gamble had clearly paid off. Against a designed output of 34,000 shaft horsepower, Triton's trials logged output as high as 45,000 shaft horsepower, giving her the highest surface speed ever recorded by a submarine up to that point. But this was only the beginning, because raw horsepower on a measured trial run in home waters was one thing. Proving that a twin-reactor plant could be trusted across tens of thousands of miles with no possibility of outside repair was another test entirely, and the Navy had already decided exactly how that test would happen. On February 4, 1960, in a secret Pentagon briefing, Beech learned that Triton's shakedown cruise would not be a routine coastal run. It would be Operation Sandblast, a fully submerged circumnavigation of the Earth, the first ever attempted by any vessel, tracing the same general route Ferdinand Magellan's expedition had sailed on the surface between 1519 and 1522. Provisions for 120 days were loaded aboard in under 2 weeks, including more than 77,000 pounds of food, and on February 16th, Triton slipped beneath the Atlantic off Long Island. In his stateroom, Beech wrote a single line for the record: "Dived and not surfacing again until May." Over the following 60 days and 21 hours, Triton covered 26,723 nautical miles at an average speed just over 18 knots, running both S4G plants continuously with no outside maintenance, no port calls, and no possibility of towing her home if either reactor failed. She traced Magellan's route almost exactly, south past the bulge of Brazil, around the storm-battered passage at Cape Horn, north and west across the vast open stretch of the Pacific, through the tight reef-strewn waters of the Philippine and Indonesian archipelagos, and home across the Indian Ocean and the South Atlantic, crossing the equator 4 separate times along the way. The only interruption to full submersion came early in the voyage, when a crewman named Poole developed appendicitis and needed emergency medical evacuation. The heavy cruiser Macon, already in South American waters as part of a separate goodwill deployment, diverted more than 2,000 miles to rendezvous with Triton off Montevideo in the early hours of March 5th. True to the mission's secrecy, Beech surfaced nothing but Triton's sail long enough to pass Poole across, then took the boat straight back down.
Weeks later, maintaining that same discipline, Triton rose only her sail again to meet the destroyer John W. Weeks in mid-Atlantic, transferring a National Geographic photographer and his film for the trip home, while the hull itself never broke the surface. A submarine that could run 2 independent nuclear plants for 2 straight months without a single reactor casualty had just answered, in the most demanding way possible, every question the Bureau of Ships had asked about redundancy back when Triton was still a set of blueprints.
Every large nuclear submarine built since Triton has taken the opposite engineering path. One exceptionally powerful, exceptionally long-lived reactor core rather than 2 smaller ones sharing the load. Modern naval reactors now run for the entire service life of a submarine without refueling, a level of reliability that finally made the redundancy Triton's designers built by brute force duplication unnecessary. Improvements in core materials, fuel enrichment, and reactor control systems over the following decades meant that a single well-engineered plant could match Triton's old combined output while taking up a fraction of the hull volume, sidestepping the entire weight distribution and cross-connection problem Electric Boat had to solve by hand in the 1950s. But Triton herself has never been matched. She remains the only Western submarine ever fitted with 2 separate nuclear reactors, a distinction she will likely hold permanently, because no Navy since has faced a mission that a single reactor couldn't solve on its own. Decommissioned in 1969 and eventually recycled through the Navy's nuclear ship disposal program, Triton's sail was preserved and now stands in a memorial park in Richland, Washington, the last visible piece of a submarine built to answer a question no engineer had ever needed to ask before. What do you do when one nuclear reactor simply isn't enough? The real breakthrough came when engineers stopped treating impossible as a verdict and started treating it as a specification, and that habit of mind is the part of this story worth carrying with you. That's the story of how a submarine designed to watch the sky for enemy bombers ended up engineering a solution so far ahead of its own requirement that it outlived the mission it was built for by decades. If you want to see what happened when Soviet engineers faced their own impossible power problem, building a reactor plant to run under Arctic ice with no Western blueprints to copy, that story is coming next, and it involves an entirely different set of impossible constraints. Subscribe if you want to keep learning how engineers solved the problems nobody else could.